right, number 2. Let's see. It says extra special hard. Okay. Not for everyone. If you're a mathlete, give it a try. All right, so extra special hard, huh? It's a bar that has a non-uniform mass density is what it comes down to. So you're asked to figure out both what is the mass of the bar and what is its center of mass. So, and we're given a density. So the bar has a density equal to A plus BX, where I assume X is someplace on the bar. It says A is a constant in units of kilograms per meter and B is a constant in terms of kilograms per meter squared, while X is the distance from one end of the bar. So if this is 0, then at that point, this little piece of density of the bar, if I was to break off this piece and measure its density would be A, right? Because that's at X equals 0. Does that make sense? And if I was to break off this little piece of the bar and measure its density would be A plus BL because the bar has length L. Does that make sense? So it's getting more dense as I go from one side to the other. That's what that sounds like. And it's linear in that the density increases in a linear fashion, directly proportional to how far across I am. We don't know the whole mass of the bar. So we would have to figure out the center of mass. We'd also have to figure out the mass of the bar. So let's blow through the series of steps that we have to do to figure this one out. It's a one-dimensional problem. So most everything we already did last time will work this time. I'm going to pick a square somewhere in the middle of the bar. I've picked a square. That square is going to have mass dm. Excellent. I'm going to start with that. I know that the bar starts at 0 and ends at, over here, this is L. So I know the length of the bar. And I have an expression for the density of the bar. First thing I need to do is find a way to point at an individual piece of the bar. Well, I'm assuming 0 is the starting point, so I'm going to choose to use X to point at that piece of the bar. There's a lot of good reasons to do so. It's linear for one. And more importantly, they already told me to use X. Right? They said X represents a distance from 0 to some point on the bar. So that seems like a good place to go. I'm going to call the size of this bar, or the size of this piece, dx. And I know that at that point, the density of the bar has to be this expression. So right now, the mass of that piece divided by dx has to be A plus bx. That has to be the density of the bar. The mass per unit length they didn't give us, but they did give us the density as an expression, which means dm equals A plus bx times dx. That is just going through the series of steps that we had for figuring out center of mass of some kind of uniform bar. It's reusing all the stuff we did before for an object that has linear symmetry. Any question about any of those choices as of yet? All right. If we're sure, then I'm going to move on. I'm going to do mass first. We need the mass of the bar. The mass of the bar is adding up all of the pieces of the bar. That's how you find the mass of the bar. I'm going to start with the piece that's at 0 and end with the piece that's at a distance L away. Now, I would like this to just equal m, but it doesn't, because I don't know what it equals. I have an expression for the density, though, so I can drop that in. Now that works, and these limits now make sense, because they are relative to dx. They tell me where I'm going to be on the bar. So I have to act on this now. It's a pretty straightforward integral. I'm supposed to integrate A plus bx with respect to x. Now, there isn't an x in this term, but this looks like a polynomial. Do you guys see that it looks like a polynomial? So there's two ways I could actually do this problem. I could break it up. I could distribute the dx and have two integrals if you think that looks better for you. It's the same answer either way. Some of you might like doing that. I don't know who you are. I know you guys who are not in physics, not in calculus, have no reason to choose one way versus another. But you can distribute the dx if it's just a sum of a bunch of terms and treat each one like a little tiny integral and you get the same answer. Or we can just find the antiderivative of all of that. It's your call. Which one? Do you guys want me to do all of it at once? Same answer. Or do you want to break it up into little pieces? All of it at once? Okay. If we do all of it at once, I do want to remind you that if there is no x and we're integrating with respect to x, then you put a placeholder for x there. We did this way back in first semester, so I'm going to put x to the 0 power there. So this will be the integral from 0 to L of ax to the 0 power plus bx to the 1 power dx. I'm doing way more than like I would do it if I was just looking at it myself, but I want to make sure that you realize that when you're finding the antiderivative of a polynomial, it's a formula. We know that's a polynomial because we're adding things together that have x in them. And I put the x's in here to remind us that it's x that's important. A is just a constant. So the a is like any number out front. It wouldn't be a part of this. I would just pull it. I can pull it out in front of the integral if you like. But because I'm doing it as one function, I really can't pull it out in front of the integral. But it doesn't get involved with the antiderivative, meaning I'm going to find the antiderivative of this term first. I'll write the a down because it's a constant. And then I will follow the procedure for a polynomial, which is add 1 to the exponent and then divide by the new exponent. So that's going to be x to the 0 plus 1 divided by 0 plus 1. Plus. Same thing, I'll drop the b here. It's a constant. I'm going to add 1 to the exponent and divide by the new exponent. And watching who's writing this down, we did this one. We did this one already. But doing them both isn't a lot to me. I think it's good practice. And that's it. That's the integral. So I will bracket this from 0 to L. This has got to be the mass. And so now I need to put in my top limit and subtract it from putting in my bottom limit. So my top limit is L, so this is going to be AL plus 1/2 BL squared minus A times 0 plus 1/2 B times 0 squared. So I put in my top limit and put in my bottom limit, subtracting them. And so the mass of the bar is AL plus 1/2 BL squared. And that's it. That's all we can do. We were told that A is in kilograms per meter. I'm bringing this up because our answer needs to be in terms of kilograms. And B is in kilograms per meter squared. Do you notice that our units for our answer is going to be kilograms? Right? Because I'm taking kilograms per meter and multiplying by something in meters. I'm taking something that's in kilograms per meter squared and multiplying by meter squared. So this is kilograms. That's good. But that's the mass. Of course. And now to do the top part of the fraction. The top part of the fraction is the integral of r dm. So all the work we did for dm and all that is still the same. The only thing we have to recognize is that we're going to change this to be the integral from 0 to L of x dm where dm is a plus bx dx. Everything is the same, except we're subbing in this where dm goes, and we already have a weighted average. Because remember, this is weighting it for where the actual mass is. Now, this is very similar to what we just did. I'm going to start by distributing the x, and I'll get from 0 to L, ax plus bx squared integrated from 0 to L with respect to x. So I assume you need me to go through all of it. So I'm going to start again by doing the antiderivative. I'm going to drop the a, add 1 to the exponent, x squared, and divide by the new exponent, 2. I don't want to write the 1 plus 1 this time. Can I just add the 1 in my head? Is that okay? Plus, drop the b, add 1 to my exponent. It's now cubed, divide by 3. And then I'm evaluating this from 0 to L. Can I interest you in not putting the 0 in, because it's just going to zero everything out, and just put the L in? I mean, it just saves me time. A L squared over 2 plus B L cubed over 3. I mean, I guess I'll write it all out, because I would hate your notes to be incomplete and be told that I'm, leaving stuff out. I'm really not trying to. So the whole right part, this is just all 0. And I get AL squared over 2 plus BL cubed over 3. This is the top part of the center of mass formula. The bottom part was what we just found a moment ago. This is the mass. So the center of mass, X center of mass, will have AL plus BL squared over 2. All right, so now we've gotten someplace. Believe it or not, there's not a whole lot we can do here. I get rid of the one L. There's an L that we can factor out on top and bottom. So I would do that. So you'll get AL over 2 plus BL squared over 3 over A plus BL over 2. But that's really about it. You can simplify this a little bit. It's nothing pretty, but you could simplify it a little bit. You could multiply top and bottom like by 2 or even 6 to get rid of all the fractions if you want. If you multiply top and bottom by 6, you'll get 3AL plus 2BL squared over 6A plus 3BL. But I mean, there's nothing else you can do. That's the limit of what you can do to simplify this. So it's not pretty, but this would be where the center of mass is. Where is it? I don't know, somewhere in the middle of the object, but closer to one end than the other. Could you figure that out? Yeah, put in some numbers if you want. Make it a meter stick, so L is 1. And pick a value for A and B. You should look at the units and see if the units work out. It should still be just meters for our units, and it is. You should check it out. This is an exercise in trying to see if you could redo the problem, but with a linear density that was not uniform. I think this is top level, probably hard, because even uniform density figuring out is tough. I will tell you though that this part, once you realize you are replacing dm with something that represents location, if you can get that through into your head, that's it. Once you do that, it's just substitution. But not necessarily easy. All right, number 7. Attempts to simulate 4Gs, making people feel as though they are accelerating at 40 meters per second squared. Each car is attached via a spoke from the center and is spun in a circular path. The spokes are 5 meters long. That's the radius of the ride. What angular speed in RPMs is required to achieve the desired centripetal acceleration? All right. I think we talked about this the other day in class, but anybody ridden this recently? I haven't either. They used to have vomit bags on the ride. Did you know they had to stop putting logos on it because people were just stealing the vomit bags to sell them? So they put just plain brown vomit bags. I find it silly that people would go on the ride just to steal the vomit bags. You know, the free stuff they give away is a vomit bag at Disney. But all right, it's going to spin. The people in the ride, we are looking top down on them. They're going to experience the acceleration in this direction because it's a centripetal acceleration. And we want that to be 40 meters per second squared. I'm going to use AC equals omega squared times R. It makes the most sense since they want my answer in RPM. This will give me my answer in radians per second, but that's still better. It's easier to convert that than the velocity. So I'm going to do this in angular. We want the centripetal to be 4 Gs or 40 meters per second squared. That has to equal omega squared times 5. So that means omega is going to be the square root of 8 radians per second. We need to convert that to rotations per minute. So if that's radians per second, the first thing I would do is say 60 seconds for every 1 minute. And then it's in radians, so I want it in rotations. So every 1 rotation is 2 pi radians. I don't know what this is. I'm sure I could bang it away, but 8 square root times 60 divided by 6.28. I got 27 RPM. Anybody else get 27 RPM? Woo! Is that it? How many rotations? Oh no, that's not it yet. If the ride can get up to speed in 7 seconds, what is the angular acceleration of the ride itself? If you can get up to that speed in 7 seconds, then I'm going to use the radians per second for my next part. And I'm going to assume that the initial velocity was 0, time was 7 seconds, and I'm interested in alpha. So that's going to be omega minus omega naught over t equals alpha. And so that's going to be the square root of 8, which I keep saying, but that's 2.8 minus 0 over 7 has to be the acceleration in radians per second squared. So 0.4. Any questions yet? We good so far? Alrighty. How many rotations do they make getting up to speed from rest? I just think we can find delta theta here and convert that answer to rotations. That seems like the way to go for me. Is that okay with you guys? So I'm going to use omega squared plus omega naught squared equals 2. No, I'm not going to use that one. Why would I do that one? I'm sorry, that's a misdirect. That's Mr. Shelton not thinking it through. I want delta theta equals 1/2 omega plus omega naught times t. I think that's the best one to use. So this would be 1/2 2.8 plus 0 times 7. I have no idea what that is, but that's in radians. So 0.5 times 2.8 times 7. 9.8 radians. So it barely moves, right? Because that's not the answer. We need number of rotations. So I'm going to divide that by 6.28. And I get a 1.6 rotations. It's that 5 meter radius that's really making it so you don't have to spin very fast. I wonder what the actual radius is. The The last time I wrote it was a long time ago. And it's not like they let you wander around that chamber and see how long the arms are. But I think it's only about 2.5, 3 meters away. Because you spin a lot faster than I'd like to. Like I said, it messes with my head a little bit. Example. So, all right. I'm ready to go. Question A. On the circles below, draw vectors representing the forces acting on the sphere just after it is released and after having been falling for a long time and reach terminal velocity. Give each vector a description label. All right, so the first one, A number 1, is just after it's released. So there will be one force acting on it, and that'll just be gravity. And number 2 is after it's been traveling for a long time, so there'll be 2 forces on it, and they will be equal, and it'll be mg and kv. Any question about that? All right. Determine the terminal velocity of the sphere. Well, that is an extension of number 2, because that's when we're at net force equals 0. Terminal velocity means the velocity is no longer changing. It is a constant, and that's when the net force is 0. I'm just going to throw that out there. You might want to put a box around that, because that's how they're working it in. You need to know that it's terminal because it's no longer increasing. Whenever something's no longer changing, that's a net force equals 0 problem. So kv minus mg equals 0, or v equals mg over k. That is the terminal velocity. I'll put a little t there to remind us that's terminal velocity. All righty, I bet they're going to ask more questions. C. Draw the following 3 graphs for the sphere's motion, clearly showing significant features of the motion just after the sphere is released, as well as after a long time. So this one might be tough if we hadn't talked about it. Notice, you're not asked to derive anything yet. You just have to draw the shape of the graphs. So, let's start with the one that we kind of know, and let's put them like right here. There's acceleration and time. Velocity and time. Displacement and time. Now, consistency probably matters here. I don't know how they gave the points on the actual exam, but I'm noticing that the graphs have both a positive side and a negative side. So is downwards positive or is downwards negative for you? I think as long as you're clear, it shouldn't be a problem. I kind of already set the precedent and made downwards negative because I made the weight negative. But I don't really care. You could choose either one of these. I'm going to focus on this one first because we kind of did this in class already. We know that it's going to reach a terminal velocity that's asymptotic, meaning it's going to kind of come close to this but maybe never reach it. We know that it's going to be based on the exponential. So your graph needs to start from 0 because the velocity started at 0 and approaches this velocity. Now, this one might be harder, but when we first release it, the acceleration is g. Right? There's no velocity, so the net force is just the weight. So its acceleration is the acceleration of gravity. And after a long time, it reaches a steady state condition where it's no longer accelerating, so it's going to go to 0. What's the most likely way that'll happen? Well, it's probably similar to the velocity in that it's asymptotic. Meaning it'll approach 0. Well, that wasn't great asymptote, but come on. There, that's a good asymptote. Didn't prove this, but does that seem likely? I think it seems not unreasonable. I think this one is the harder one, though. X is a displacement. How would you draw it? Well, it starts from I don't know, the origin. Now, this one might be tough. There's going to be a time when it really becomes a constant velocity, which means the position versus time graph will be a constant value. The slope will be. But it doesn't get there right away. In the beginning, it's accelerating, so it's going to ramp up and then somewhere transition where it'll be a straight line. So it curves for a little bit, and then there's a straight line. In fact, when we do this lab later this week, perhaps, you have to wait until the coffee filter makes it to a point where it's traveling at a constant speed and then measure the velocity at that point where it's constant. All right. I think this one was probably the one that would be tough. I think the other two aren't so terrible, but this one might have been tough. I think they gave like 2 points per graph. So I'll point out, at this point in the problem, I think it's 2 points per graph. So 2, 4, 6. I think it was 1 point each for these. So that's 8. And then 2 points for this, 9, 10. So 10 points of this FRQ is before there's any calculus involved at all. Now, you might not have gotten all the graphs right. I'm not saying you did. I'm just saying that when we talk about how they're going to assign points, they're going to have lots of other ways for you to get points, but there's going to be points assigned directly for your ability to do the integration too. So that's got to be coming up. Oh, no, that's it? Oh. All right. So you never actually had to do it, so this must have been worth more points than that. So either I cut off the problem or that was it. Oh, well. I mean, I want to do the other part now. I was all excited for it, but it wasn't part of your homework. So I think you have this in your notes, though, right? We did this exact same one. So I thought that was the next thing. So either it got cut off or I didn't pay close enough attention. You should go home and find v as a function of t. You should work it out. And the answer ends up being mg over k times 1 minus e to the negative k over m times t. So you should do that and show this to be true. That's what I expected you to do. And let me, can I show you something else without it being too much of a burden on you guys? The acceleration is dv dt. It's the derivative. I don't know if you guys can do this derivative or not. You should try. I'm going to work the derivative out. I want to see if you can follow along. To do that, I'm going to take the expression and I'm going to distribute. So it'll be mg over k minus mg over k e to the minus k over m t. Just distributing. Because then when you take the derivative, we did this first semester, but it's been a while, you distribute. So I can take the derivative of this term first, and then subtract the derivative of this term next. Now this looks way more complicated than it is, but it has complications. And these complications are tough. The first one, though, just 0. There's no t in it. So it does not change with respect to time. So that whole term is 0. Let's focus on the next part, though. Mg over k is a constant. So minus mg over k, and now it's the derivative with respect to time of e to the minus k over mt. Do me a this is all the stuff that's A. So its derivative will be all of that stuff out front minus k over m e to the minus k, e to the minus k over m t. Now, do you notice k cancels with k, m cancels with m, minus signs cancel? And our acceleration equals g e to the minus k over m t. I get it's law of math. But what does this look like? What is the acceleration at t equals 0? It's got to be g. If I put 0 in for t, it's e to the 0. E to the 0 is 1. So this has got to just be g. And what is the acceleration when t becomes really big? Can you estimate that one? It's got to be 0. Thank you. Because it's going to be 1 over a really big number. So that's going to be 0. It's like an asymptote still. I don't expect everybody to catch on to this, but I think this is achievable. I know it'll be achievable through practice. We'll practice a little bit every homework assignment. I thought that there would be more to this one, but not so much. All right. Was there anything else on the homework? Yes, ma'am. Number 4. A 4 kilogram cart travels at 5 meters per second to the right towards a 10 kilogram cart traveling at 3 meters per second to the right. But a third cart of 3 kilogram is traveling at 4 meters per second to the left. God. What is the velocity of the center of mass of the system? Okay. So velocity of the center of mass. Do you remember talking about this in class, how to do it? So it's going to be mass times V1 plus mass times V2 plus mass times V3 all over, well, mass 1, mass 2, mass 3, all over mass 1 plus mass 2 plus mass 3. So let's just knock this one out of the way first. 4 kilogram, and I'm going to make to the right positive. So 4 times 5 plus 10 times 3 plus 3 times negative 4, all over 17. So that'll be 20 plus 30 minus 12 over 17, 38 divided by 17. So I get 2.2 meters per second. So center of mass isn't moving very much compared to everything else. The 4 kilogram and 10 kilogram cart have a perfectly inelastic collision before coming in contact with the 3 kilogram cart. What is the new velocity of the center of mass? 2.2 meters per second. It won't change. The velocity of center of mass should stay constant unless acted on by an outside force. Now, you could have done the collision problem first to show that, and that's fine. Would you like me to do the collision problem and show that that's going to be true? Okay, so it won't take long. So it's just the first 2 cars. So that's going to be 4 times 5 plus 10 times 3 equals 14 plus whatever this final velocity is. This is still 50 divided by 14. That is the new velocity. Now, to find the velocity of center of mass, it's now just 2 cars. 14 times whatever 50 over 14 is, minus 12 over 17. And obviously that's still going to be 2.2 meters per second. All right, so some of these will be appearing twice in this video. That's fine by me. I don't care. Number 2, extra special hard, not for everyone. If you are a mathlete, give it a try. We have a bar of non-uniform mass density. So there's the bar. And we're told that its mass density is A plus bx. And that the bar starts over here. X is measured from one end of the bar. And the bar is L long. So if I was to break a piece of the bar off over here, what would its density be right there at the edge? It would be A. That's right. That would be the density right at the edge. And if I was to break a piece off right here, right at the other edge, what would its density be? What's that? A plus BL. And it gets more dense as I go from the left side to the right side. Right? So our job is to do two things, actually. We're supposed to find the center of mass. But truthfully, we can't find the center of mass without finding the mass of the bar, which was not given. So you could put the bar on the scale, but they probably want something else. So we're gonna have to figure out the mass of the bar first, and I want to do that first because it's nice and relatively straightforward, and it's slightly easier than finding the center of mass, which will use the information we use for finding the mass of the bar. So just a reminder, the mass of the bar would be the sum of all of the pieces of mass. All right? Summed up over the whole bar. So I'm going to break the bar into lots of little pieces. Let's identify a single piece from the bar. There's my single piece, dm. I need to find a way to point at this piece. So it seems kind of clear that the way I'm going to have to point at the piece should be using a variable that comes from the expression for the density of the bar. It tells me to use x, so I'm going to use x. My piece of bar is a distance x away from one end. So how big is the piece in terms of the measurement we are using? Our piece would be dx wide. Therefore, the density of any piece of the bar should be equal to dm over dx. But this is a function. Different pieces will have different densities. So I could write dm as lambda dx, or better yet, I could write it as a plus bx dx. That is what dm is. Every piece of mass has a different mass. Aw, that was my phone. Thought I broke it. Did I broke it? Kind of desperate to break it so I can get a new one. That's why I've been like, no case in my phone. But unfortunately for me, I did not break it, which means no new phone. No. I'm not desperate. Here we go. So, if you want to figure out the mass, you're going to have to take all of this and sub it in for dm, and then add up all the pieces from one end to the other. So, a plus bx dx added up from piece 0 all the way to the piece at the other end. You just have to do the work here. There's a lot of stuff, but there's not much here. Getting to here, I think, is the hard part, by the way. Actually executing this integral, not interesting even a little bit. So we've already done this integral, or something similar to it, so don't feel too bad. You can do this two different ways. You could treat the whole thing as one expression, one polynomial, or if that scares you, you could break it up into little mini integrals. Because you're adding, and integral by definition is a sum, then you can break integrals up into individual sums. Right? It's just adding up numbers. That's all an integral is. So if you're adding two sets of numbers, fine. This might be easier for you. I'm going to do the problem this way because earlier in class, in the other class, I did it as a full expression. And so this way, I'm just going to do it this way to prove it's the same. We good with that? All right. So this is going to be, I can take any constant out front of an integral because every single term in the sum is being multiplied by a or b. So I could write this as a integral dx from 0 to L plus b integral x dx from 0 to L. So, I know I have to do this for some of you, so I'm going to. If there's no number here, then that's a 1, or x to the 0. And if there's no exponent, then put a 1 there to make it x to the 1. So it's a polynomial. I do the thing where I add 1 to the exponent, divide by the new exponent. So this is going to be a x to the 0 plus 1 divided by 0 plus 1, evaluated from 0 to L, plus b times, all right, same thing here, x to the 1 plus 1 divided by 1 plus 1, evaluated from 0 to L. And look, I'm watching you guys. You guys all asked me to do this. If there's nothing in your notes written from one step to the next, then why am I doing it at all? Do you understand what I'm saying? Your notes are useless to you. I already wrote all of these steps down the last time I did this in front of you. The only difference between the last time and this time is that there's this extra term with bx in it. But if you didn't know why I'm doing each of these things, and all you're doing is writing it down, look, I'll put the whole answer up there with all the stuff in it and the steps. You need to talk to yourself about why I'm doing any of these things. If you want any chance of you being able to do this on your own sometime, say like on a test. So if you're not doing that, because I watch when you write, then I'll just go at 3 times the speed, because this is just algebra. Right? I'm talking slow and deliberate, so you can add some notes. Why do we go from this step to this step? Why do we do those things that are there? That's what you should be telling yourself. But once this was done, once we got to right about here, this is a procedure, and we've done this procedure many times this year. So I don't feel particularly interested in the minutia. I definitely don't want to watch, write down x to the 0 plus 1. If you're just copying me, come on. So right now, if yours says x to the 0 plus 1 divided by 0 plus 1, you should probably put your face in the fan. Just thought. There's no explanation as to why you're doing that. Did you write in there that we can recognize that this is a polynomial, which is why we can use this function at all? That's the important stuff. If it was sine of x, it'd be different. E to the x, you'd have to do something else. You need to understand why we're doing it this way for this expression. All right, enough harping on you. It's your homework, your test. This is going to be a to the L minus a times 0, putting in my limits, plus 1 half b to the L squared minus 1 half b to the b times 0 squared. So this whole thing just becomes AL plus BL squared over 2. And this is the mass. Am I sure it's mass? Well, A is in terms of kilograms per meter, and B is in terms of kilograms per meter squared, as expressed in the problem. Assuming L is in meters, my units work out to be kilograms, so that suggests we're okay. What? We're doing more than that. We are replacing the x. That was the placeholder. We were integrating with respect to x. And x had to start at one end of the bar, 0, and end at the other end of the bar. We were told that was L. So putting in the limits means that we put in the upper limit as our starting limit, and put that in for every instance of x in your equation. And then we subtract what happens when you put in the lower limit for every instance of x in your equation. That's what putting in the limits means. Oh, you're welcome. I want those kinds of questions because it ensures that you understand why we do the steps the way we do them. All right, that's the mass. We need that to actually find the center of mass, because center of mass is actually, x CM is the integral of r dm over the integral of dm. We just did the bottom part of that. We got to do the top part now. So let's do the top part, which is going to be the integral of x dm. R is a placeholder for displacement from your reference point. We're doing a one-dimensional center of mass, so x will be the placeholder. I don't have to explain this next part. We're still going from 0 to L, where dm is going to be a plus bx dx. All is the same, right? We're replacing dm with the same expression. So, continuing. Yes, sir?
Could you not plug in for, instead of a plus bx dx, could you just plug in what you got from the mass?
No.
No?
No.
Why not?
Because it won't work. dm is our piece of mass and has to be integrated, but in this expression, every piece of mass is scaled by how far away it is from the axis. So some pieces are more important than other pieces. When we added up the mass, every piece had the same level of importance, which is why it was a straight sum. But in this piece, some pieces are more important than others. Does that make sense?
Yeah.
Okay. So I know there is an idea that you could do that, but the x can't be brought out front of the integral in this instance because each x is different, and each piece of mass is a different value for each x. That's why we have to put in our expression that's in terms of x and then integrate. What we're going to see right away is that we have a new integrand that's ax plus bx squared that must be integrated from 0 to L. We all good there?
Yes.
Now, I could do this the same way I did it last time, meaning I could distribute the dx and do this as two separate integrals. This time, I'm going to choose not to, purposefully, so that I can show you that you can take this as a term and just use the polynomial rule on each term. And that's what I'm going to do. So, ax is ax to the 1. That will be ax to the 2 divided by 2. And bx squared integrates the same way. Add 1 to the exponent, divide by the new exponent, and then I need to evaluate this from 0 to L. Yep. I probably would. I'm putting every step in there because I think most of the people in the room need to see it. All right, so I'm not even going to bother to put in the bottom limit. It's 0. We already know that that's going to zero everything out. So this is going to be AL squared over 2 plus BL cubed over 3. This is just the top portion of my center of mass function. I still need to add in the bottom function here. So if I want the center of mass, I'll have to put in AL plus BL squared over 2. That's now the center of mass. So this was the integral of x dm, and this is the integral of just dm. There's an L in every term here, and we know it's non-zero, so we can factor out the L that's in every term. So you get, AL over 2 plus BL squared over 3, all divided by A plus BL over 2. There's really nothing you can do to make this prettier. I mean, yeah, you could factor out one of the L's on top. It's kind of nice maybe to do that, but it doesn't really give you much that you can just get rid of because all the coefficients are different. The only thing that factoring out the one L will do is ensure that you recognize that you're going to have something in kilograms top and bottom that cancels out, and your final answer will be in terms of a length. But if you don't care about that, you can multiply by like 6 and get 3AL plus 2BL squared over 6A plus 3BL. For those of you who hate to have a complex fraction. But you're not gonna make it nicer than this. This is it. So, in exercise, yeah. I said this earlier, but you guys had lots more questions. So number 4. That's the one with the 3 carts. And you're supposed to find the velocity of the center of mass. That's just m1v1 plus m2v2 plus m3v3, all divided by m1 plus m2 plus m3. That's how you find velocity center of mass. We talked about that a little while ago. This problem is intentionally designed to have you have the cars interact and show that the velocity of the center of mass never changes. So there's a collision that takes place between 2 of the cars. You're supposed to show that the velocity of the center of mass is still the same. It doesn't say that in the problem, but that's what you should get. So this ends up just being, 4 times 5 plus 10 times 3, and the other cart is going the other direction, so that's 5 times negative? 3 times negative 4. So 2 carts going to the right. I have made to the right positive, and then this is just 4 plus 10 plus 3, that's 17. So that's 50 minus 12, 38 over 17. That's 2.2 kilograms meters per second. So yeah.
Is it better to put it in fraction or decimal?
I don't care.
Don't care.
You have a collision that occurs between the first 2 cars. So M1V1 plus M2V2 ends up equaling M1 plus M2 times their combined velocity V. In this collision, this is still going to be 20 plus 30 equals 14V. So V is 50 over 14. I'm going to leave it like this so that you can clearly see that in the velocity center of mass, you're going to have M combined, which is M1 plus M2, times their combined velocity plus m3 v3, all divided by 17. So this has got to be m1 plus m2, 4 plus 10, times their velocity, 50 over 14, plus 3 times negative 4, all over 17. That's still 50 plus negative 12. That's still going to be 2.2. Why doesn't the collision affect this? Yes. Not momentum. So let me make that very clear. And then your next question was direction. And yes, you should probably say that it's to the right because our answer came out to be positive. So this, whatever's happening, our system is slowly drifting to the right at 2.2 meters per second. It doesn't matter whether there's 3 objects or 1,000 objects. If there's no external net force, the individual interactions do not change the moment of inertia of the system. So the only way to do that is to have an external net force. So the old adage, if you have, 2 astronauts in space and they're going to play catch with a third astronaut and one of them is going to be the ball. Well, the velocity of the system is 0. The momentum of the system is 0. After the first guy is thrown, the second guy is going to be moving too, but the velocity of center of mass of the system is 0. There's generally only one throw, though, isn't there? Because he's going to be drifting away forever in one direction. And even if they catch each other, if they join together, they're going to be drifting away in the other direction, but the velocity of center of mass is still 0, even though they're now moving. Now, the energy of the system can change. The energy can change. It does change all the time. But the momentum doesn't necessarily change. Things can stick together, stuff like that. Bounce off of each other. All right. Is that enough for number 4? Yeah. A 20 kilogram mass hung on a 2 meter string is at rest at ground level. A 5 kilogram mass sliding across the ground at 10 meters per second collides with a 20 kilogram mass. In one collision, the masses stick together. In another mass, the mass bounces backwards off the 20 kilogram mass. In which case does a 20 kilogram mass make a larger angle with the vertical after the collision, and why? Create a written justification, then prove it using clear results from a perfectly inelastic collision compared with the case in which the recoil velocity of the 5 kilogram mass is 3 meters per second, in which case is the most energy lost. Holy crap, that's a lot of work. It's going to be the one in which the mass bounces off, and it should be obvious as to why. I say that knowing that for some of you, very little of this is obvious. So let's consider the situation that's being indicated. So I've got one mass attached to a string like so, and the other mass is approaching it, and in one case, they're going to join together in that collision. So there's this just beforehand. Well, that didn't work out to be speedier, but oh well. So this is our secondary case. This is our primary case. In the first case, this system swings upwards, right? So then there's the case where it bounces off. And in the case where it bounces off, I'm just going to just duplicate that again. In the case where it bounces off, just this one. This one's going this way after the collision. In which case does the angle greater? This case will be greater than this case. Why? Quite simple. In which case did this box have the larger change in momentum? When it sticks to the first box or when it bounces off of that box? You should ask yourself that question. It's the most important question here. In this case, the box is merely slowed down. In this case, the box is stopped and returned back in the other direction. It's a larger impulse. We are talking specifically about impulse here. So when it is stopped, turned around, and sent back, that's a bigger impulse, which means this box gets a bigger impulse, a bigger change in its own momentum due to that collision, which means it'll be traveling faster after that collision and will therefore swing upwards more. It has more energy. I think to have a full description, you need to make sure you understand that the impulse is the thing that determines how much velocity the second box has after the collision. The one where it has more impulse is the one where it's going to have more velocity. And from there, that means it has more energy. And from there, it means it'll convert that energy into gravitational potential. It's going to have to be higher. Now, you got to prove it? Well, good luck with that. Prove it. If you need me to do one of those cases, I'll do one of those cases. You pick which one, because I'm not doing both. Fine. So the momentum of the system before the collision is a 5 kilogram mass at 10 meters per second. So the momentum of the system is 50 kilogram meters per second. After the collision, the instantaneous moment after the collision, which is, we're talking about just the moment before that mass begins to swing, its velocity, unknown, this one, 3 meters per second. So that momentum is going to be 5 kilograms times negative 3 meters per second plus 20 kilograms times my unknown velocity v, and that has to equal 50 kilograms meters per second. That is the momentum equation for that collision. Any question about what I've done there to get the momentum equation for that collision? 3 times 5 is 15. So this is going to be 65 equals 20V. So V is going to equal 3.25 meters per second. So that's the velocity of the 20 kilogram mass after the collision. The kinetic energy is therefore going to equal gravitational potential energy, assuming it's all kinetic. The kinetic energy I care about here is just the kinetic energy of the 20 kilogram mass. So that'll be 1/2 times 20 times 3.25 squared. And that's going to equal mgl times 1 minus cosine theta. They asked for the angle. So you need to make sure you find the angle, not the height. Sound familiar? Yes, sir.
So 3.25 is in meters per second because you're turning it from kilogram meters per second by dividing for 20, which is in kilograms.
Huh?
Well, okay, you're starting off with, on that side, you're starting off with 50 kilogram meters per second as your units. And you're ending off in meters per second.
Yes.
Is that because you're dividing the 65 by the 20?
Yes.
Different units? Okay.
Yes. Because this is 20 kilograms, right? And V will carry with it whatever the units are that are left over. And this came from 5 kilograms times 10 meters per second, right? First box.
So kilogram meter per second is kind of a unit for momentum?
Not kind of, it is the unit for momentum.
I haven't seen us use it before today.
I'm writing it out not to be mean, but to remind you that all of our units are actually complicated units. All of these are different units we will use in this class. Some of them have more meaning than others, but all of them have a meaning in that they represent something. Some of them have other names, like this is a Newton. This is a Newton meter, therefore a joule. This is a joule per second, also known as a watt. And this one don't have a special name. But you can get these other ways. This is also a Newton second, which I did not go into, but would be the result of calculating impulse using force and time, which we did talk about. But the unit generally for momentum is kilogram meter per second. But Newton second would work too. Okay? But all of our units are some gross combination of kilograms, meters, and seconds. The KGS system or MKS system. No worries. I'm kind of a mind that I can go ahead and stop here. This is 20, 10. I don't know what the length of the string is. 2 meter long string. 1 minus cosine theta. And whatever that is, that's the energy here. So you can solve that for theta. Just be careful. All the 20 cancels out here. That's fine. When you're solving for the angle, make sure that your height isn't more than 4, because if so, your angle goes all the way around. In the other collision, your mass will be more because both masses are joined together after the collision. All right, that was number 5. And we're not going to have time to do any more. But we have an expression for the velocity. And I asked the question, what would happen if you took the derivative of the velocity with respect to time to get the acceleration? You should consider that. You should look at it. Some of you it'll be no big deal. Some of you it'll be challenging. You should look at the result. Earlier in the year, you could use an example like this and try and find the the center of mass of this. This would be more interesting. And it would have a linear density that would be proportional in some way to x. So there'd be some proportion here. And if you know anything about geometry, you could probably work out what the proportion is, how much each piece of mass would have as you went across. God, I'm knocking everything around my desk. How much each piece of mass would be based on starting here at 0 and here being some finite value. You could do it. It's not hard. You guys who have some geometry skill, take a look at it. You're gonna get this. This was actually on the AP exam one year. They gave this expression for a triangular spoke, and you had to find the moment of inertia and center of mass of the spoke. It's about 6 years ago. So it can be asked, but they gave this. You didn't have to determine this. So, but I bring it up because that's why I gave you the question you just had a moment ago. That ends up being kind of nicer, though, when you work it out, because its proportionality constant ends up being proportional with L in it for the length of the spoke. So it's not some generic A and B. But, all right. You see it? It's right there. It says if you have a function, e to the ax, the derivative will be whatever a is out front and e to the ax. It's on your equation sheet. We've never done this derivative before. I'm just picking this one out of the equation sheet. You guys see it okay? Can we apply that to what's over there?